With this broad kind of a background, let's try to answer the question where we started with, which is that I'm dealing with the word robot, so I need to be able to say what is the hardware. And there are normally, of course, two types of hardware as we looked at into the brief of AI, the one which is sensors and the other one which is the actuators. So AI is still that I look at the world from the sensors, so that's my environment. And this is currently my physical real robot, previously an AI agent, and I act with the help of actuators. So the sensors help you look at the world, and the actuators help you actuate or manipulate the world. In terms of actuators, typically you have a robot like this, which has one wheel here, the small wheels. The wheels don't cost. Driven by a DC motor, which also doesn't cost. And if you want to move forward, turn both of them in the forward direction, and your robot will go forward. If you want to rotate, turn this forward and turn this backward, and your robot will turn like this. So that's simple kinematics. So this is what is a typical setup. It's called as a differential wheel drive system. It's called as differential because basically the linear speed by which you move is the linear speed of the left wheel, the linear speed of the right wheel, and the angular speed by which you move is given by a differential. So that's where the differential comes from. That's the distance between the wheel. So the angular speed is based on a differential. Those are what are my typical actuators. Now, depending upon the application, and I mean the swarm robots basically move. Now I took in some examples where litter had to be just picked up, and sometimes the robots need to form a physical chain. So one robot needs to be attached to the other one. There's actually another actuator that doesn't really cost us anything, and that's a small clipper. So it goes clip. And you know why doesn't it cost anything? Go out where your clothes are drying. They are held by clippers. So all you need is another one small motor which does clip. That's a very easy mechanism. That's a very cheap mechanism. So it's just a clipper. So all that will happen is that in case of physical chaining, the robot will come very close to the physical robot and do a clip. Or if this is the litter, the robot goes it comes very close and it does clip. Sometimes you need a better clipper, and that is what is called as a manipulator. Which is of course another course, with a difference that the manipulator which were taken over there again cost in lakhs of rupees. That's a very high amount, but then those cost lakhs of rupees because of course of their payload capacity and their precision in calculating the joint angles and their carbon fiber bodies, which gives a high strength and a low mass, and all the factors that you should be aware of. Now, this is just plastic, so plastic doesn't cost, and sometimes fully actuated, sometimes under actuated motors. So let's take the worst example. Let's take the most expensive, fully actuated, just a DC motor. Plastic is not going to cost you anything. There are problems that you are already aware of. I always only approximately know my position. Sometimes I need to deal with open loop controls and pray that the errors don't increase too much with time. But then those are valid things to do. So it become, and of course the end effector will be the same clipper. So that's your clipper. So in that case, the manipulator hand can go a little bit and do clip. And to prove that there are manipulators possible around that 100 rupee mark, just go to a local robotics store. They'll have all those cheap manipulation options. Just don't ask the vendors the questions which you would have asked otherwise about accuracy and repeatability and the payload. So Lita is extremely light. That's all that this robot can do. So those are extremely cheap or extremely low cost actuator. Of course, you could also have small drones, which was my aerial robot. So the fans which are over here. And again, you need, I mean, I let you decide what is the difference between a high cost drone and a low cost drone in terms of the technical parameters. So I mean, you can just take a very thin material, add in a few motors over here, just connect them all up, and this becomes your extremely low cost drone. Okay, so those are the kind of hardware that we are dealing with. And in terms of the actuators, every actuator will need a power. So this is something that is most important and rarely talked about. So it's the power system. And that's one of the answers why all this thing becomes important, because all that you have a space for is an extremely small battery pack. So don't even imagine the kind of battery packs that you now use for your mobile phones, which may still be on the heavier side. So you need extremely light battery packs. Otherwise, the battery pack itself is heavy and the payload increases, and your robot has too many problems already because of low cost hardware, which of course limits the maximum amount that the robot can do. More important in case of drones. So a swarm robot, the robots will often come for charging. So you don't have to operate swarm robots for decades and for years and for centuries without charging. They'll do their bit with the power system and they'll come back for charging again. But then that's exactly where the choice of hardware comes into play. So we took all low power actuators as of now. That's why we're keeping the payloads and everything low power motors, and of course in terms of sensors you'll again see, and we don't have a heavy GPU based system on board which takes a lot of power. So even though the battery is extremely small, the power system is still sufficient to drive the robots because the devices are not power intensive. Now of course there is research into swarm robots which can charge on the fly, as in use solar and all those energies that are into the environment. I'll not speak about that. Let's directly come to the sensors, which is a whole lot interesting. Now, in any application, the choice of sensors is basically dependent upon the utility of the sensor. So if it was expensive robots, some robots are driven by vision, which are video cameras, what I'm pointing to, which is recording my face. Sometimes we use just a LiDAR, which is a laser pen. Sometimes we have to use both of them. Sometimes we need to use 3D sensor, sometimes 2D sensor. It all depends upon the application. And that's why you don't have even a single sensor suit for all robots. And that's why I'm asked this question quite a lot, and I still fumble upon answering it up. Which is the best sensor suit for robots? It depends upon your application. If I don't know the application, it's extremely hard to comment. Cost is not the only criterion. So let's first fix in some requirements and then come to sensors. Now, our basic emphasis should be something like a social potential field. So the robots need to display some behavior. So the most basic behavior was a social potential field. So, and because I'll derive all the behaviors that I'll be discussing based on social potential field only, so all my sensors will just enable me display social potential field. As long as I can have social potential field, I'm happy with that. Now, this was also a big behavior, so let us first take in attraction to goal. I'll replace goal by other agents and it'll become attraction to other agents. When they are far away, it will become the other force of social potential field. So I should be able to calculate attraction to goal. Now, attraction to goal was given by two terms. So basically, it was distance between the robot and the goal and times the direction. So direction was g minus q divided by distance between q and g. This was the magnitude, this was the direction. And therefore, let us say the inputs are previously what I said, that I need to know g, which is fixed. In Swarm, I'll have to really say, how do I know that? But then in terms of actual, the physical real robot, I had said that goal coordinates are always known. And I needed to know Q. So there I had said that I use a localization system. So this was based on localization. And this was some complex HRI and goal to coordinate mapping, or and then I can get everything. Now the problem is, if I take any sensor that solves a localization problem, none of the sensors is really cheap. So most of the sensors that give you accurate localization are actually pretty expensive. That's why you use a LiDAR that gives you accurate localization. Localization is the number one problem. And therefore, I cannot just increase the cost of the robot. And because I cannot increase the cost of the robot, I'll have to use a sensor which enables me to compute this thing pretty easily. So I rewrite this equation in a simpler format. I don't need to know the location of the goal. I just need a vector to the goal. And now let me take in a sensor. So the first way that you could do is, you say the goal is a bright red light. Okay, just because I had a red color marker. Marker? Okay, that's what we use in physical classes. Doesn't mean I should write down red. So this thing, and that's fair. So in all the application, I want the robot to reach to a place. So that's my place of interest. So I'll take a light bulb and I'll just put it over there. Simple enough. And what I'll do is, this is my robot. I will install a omnidirectional camera. Now, if you want to imagine what is the omnidirectional camera, there are multiple ways by which you can actually get an omnidirectional camera. The first way you can get an omnidirectional camera is, this is a normal camera, there is a camera and that projects it. This is the image plane, so whatever light rays come, they fall on this. Earlier it used to be negative, now they are photochromatic receptors which are over here. The only thing that I change is I make it circular in nature. And therefore light from all sources will come, it will fall on this surface which is my photochromatic receptors. And again, people might say that I purchased an expensive DSLR camera for 50,000 rupees. It's very expensive. We're talking about cheaper resolution, extremely cheap resolution, and bad quality photochromatic receptors. And the light will come like from here. So that's my light source. The light will come, it will fall around over here, and then my receptor, which is over here, will detect it up and will send me the digital signal. Very bad resolution, again to say. That's one way. The other way to say is, of course, you know that there is a mirror, and a mirror is an amazing device. It takes light from one direction and shoots it out to the other. And therefore, what I do is, I take a mirror and make it look downstairs. These are special parabolic mirrors. So the light comes from all directions and it always goes down. And below is where my actual camera is there. So the light will come from all directions, it will cut down and my actual camera will get it over here. Again, you might say that I made a new home and the mirror wala took a lot of money. So these are special mirrors, but these are not that high cost, as in that mirror would have been extremely big. This is a very small mirror. It's just that it has a special parabolic shape that light comes in around over here and it gets down, and then you get a 360-degree view image of whatever is all around you. And similarly, of course, there's a big research into omnidirectional cameras. There are multiple philosophies by which you make them. And if you are on social media, you already look at omnidirectional images and go, wow, omnidirectional image. So I need not say more about omnidirectional cameras. So let's say what happens is that this ray comes and it strikes at this thing. And therefore I do know what is the vector to goal. And I know direction to goal. So I look at from which direction is light coming and I just go there. So I'm following a conic potential where my F attraction is given times K1 times cos theta goal, that's this unit vector, and sin theta goal. That was quadratic. This is conic, so the magnitude is constant. And theta goal is exactly this angle. So I know with respect to my heading direction, the light came at 30 degrees, so I'll try to turn and go at 30 degrees. Simple enough.